Hello everyone, this is your Electron editor. In this session, we'll go with the John Teller effect. Okay, I usually take classes for +2 level students who are preparing for NEET examination, JEE mains, JEE advanced examination. For all those students, actually John Teller effect is not at all required. Not at all required. In 2016, I think 2016 NEET paper, there was a question related to John Teller effect. It is nowhere mentioned in NCERT book, or in general also we don't teach this for JEE mains and all. Okay, but as one question is there once, so there is a possibility of asking questions. So in other materials also some few lines are given. So I just wanted to mention you what is actually John Teller effect, what is actually John Teller distortion. Okay, John Teller effect, or you can say John Teller distortion. What is this? Why this distortion is taking place? It's very simple. If you apply little logic, you can easily understand this. So let's go with this. I have given here some statements. Okay, now I don't want to make any changes in the statement, so statement is as it is. The geometrical distortion. Okay, now the geometrical distortion of a non-linear molecular system. If it is a linear system, there is no question of distortions. So a non-linear system that reduces its symmetry and energy. So because of this distortion, symmetry however going to be changed. Symmetry however going to be reduced. Symmetry is going to be reduced. Very interesting thing. And second thing is energy is also going to be reduced. When the system decreases its energy, it means it is going to be more stable. So obviously because of the distortion, John Teller distortion, whatever you are saying, that is going to be more stable. Okay, so the stability factor is going to be very interesting point here. So because of the John Teller distortion, its symmetry and energy both are going to be decreasing. This distortion is typically, okay, generally we observe in octahedral complexes. Okay, in octahedral complexes we discuss and how the octahedral complexes are formed in octahedral complexes, how the EG and T2G orbitals are getting distorted. All these lines we will discuss now. So we discuss in octahedral complexes. In octahedral complexes, there will be 4 bonds in the plane and 2 bonds. One is above the plane, one is below the plane. We call those 2 bonds as axial bonds, and 4 bonds in the plane we call them as equatorial. So there will be distortions in these axial bonds, or you can say in these equatorial bonds. Actually, all these bond lengths must be same. If it is going to be a perfect octahedral structure, means the axial bond lengths and equatorial bond lengths must be same. But sometimes these axial lengths will be more. Sometimes you can say axial lengths are small, or you can say axial lengths are small means equatorial lengths are going to be longer. Okay, so that lines we are going to use here. And so this statement, you see, this distortion is typically observed among the octahedral complexes where the 2 axial bonds can be shorter or longer than the equatorial bonds. When you compare with the equatorial bonds, the 2 bonds can be longer or shorter. So based on that, we are going to use the term elongation of the axial bonds or elongation of the equatorial bonds. Such kind of terms we are going to use. So this is John Teller effect. First point, why John Teller effect? Okay, about this we'll discuss now. We'll go with one simple example. Nickel with 6 water molecules, NiH2O taken 6 plus 2. This is the example we are going to discuss. In this, nickel is with +2 oxidation state. We know nickel is 4s2 3d8 outermost electronic configurations. Outer 2 orbitals I am writing 3d8 4s2. In nickel +2, the 2 electrons will be lost from 4s orbital, so it will be 4s0 3d8. And now when nickel is attached to 6 water molecules, OH2, all these water molecules, all these bond lengths are going to be same, 2.05 angstroms. So what we can say? Just now we were discussing in John Teller effect, equatorial bonds and axial bond lengths are going to be changing. Either they will be longer or shorter. But here you can see all are showing 2.05. Equatorial 2.05, axial also 2.05. That means there is no John Teller distortion. Why in nickel +2 there is no John Teller distortion? One more example, you see, copper H2O taken 6 plus 2. We know copper electronic configuration is 4s1 3d10. Fulfilled stability of d orbitals. Copper plus 2. Copper plus 2 means 4s 0 and 3d 9. 9 electrons are there in d orbital. So how it is going to be? D9 when it is there, copper 1, 2, 3, 4, 5, 6. In this, if you see, these bonds are longer, 2.45, and this bond is going to be 2 angstrom. Now, two different bond lengths you can see here, 2 angstrom in the equatorial, 2.45 above and below. So two types of bonds you can see, two types of bond lengths you can notice here. This is because of the John-Taylor distortion. That means you can explain this point based on the John-Taylor distortion. So the point is now, why in case of copper only, why not in case of nickel? For that purpose, you need to know the splitting of d orbitals and what actually happens when the d orbitals are already with some electrons. So we'll go with them. We know the splitting of d orbitals, 5 d orbitals split into two categories. Okay, T2g orbitals, Eg orbitals. T2g orbitals, all the 3 orbitals are with equal energy. Okay, now what the 3 orbitals are? dxy, dyz, dxz. These two are of same energy, dx square minus y square dz square. Why so? Why these are getting more energy than these? For this we say generally this is octahedral splitting. In octahedral splitting, the ligands are approaching along the axis. X-axis, y-axis, z-axis, along the axis the ligands are coming. When along the axis the ligands are coming, whatever the orbitals are present along the axis, they are experiencing more electronic repulsions. The ligand electrons, the electrons already present in the orbitals of that which are present along the axis. Along the axis, the orbitals present are dx square minus y square and dz square. We know the shapes. If you want, I will give you again. These are the orbitals we show, dxy, dyz, dxz orbitals. The 4 lobes present between the axis. But when you see this one, this kind of orbital shapes we show for dx square minus y square, dz square is baby sutra shape, we know that is very well. So this is along the axis. So in case of octahedral, the ligands are approaching along the axis. So these are getting more energy, that's why they are here, and dxy, dyz, dxz orbitals are at the bottom, or you can say T2g orbitals with lower energy. Done. So this is first point. Next, what happens? Let us go with one by one electrons. One electron present here. Obviously, according to Pauli's principle, Hund's principle, Aubau's principle, all principles we need to follow here while filling the electrons. Electron is going to come here. Lower energy orbitals to be filled first. Electron is present here. Now, look at these 3. All the 3 orbitals are now not same. Why? Because dxy, for example, let us say this is dxy orbital. Now dxy orbital is with 1 electron. But yz and xz orbitals are not having electrons. So definitely the repulsions between the dxy orbital ligands, dyz and xz orbitals and ligands will be definitely different. Right? So dxy orbital is going to experience more repulsions than yz and xz. Because of this, there will be definitely some difference. Okay, the dxy orbital is going to experience more repulsions. More repulsions when it is experiencing, its energy is going to be increased. But the advantage is, in our case, in octahedral case, the ligands are coming along the axis. These orbitals are present between the axis. Because of this reason, even though electron is present here, these are not with the electrons. This is different from the remaining 2 because of the number of electrons. Definitely distortion should be there, but the distortion is not so significant that you can notice, that you can recognize. There is no need, because here the ligands are approaching along the axis. These are present between the axis. Definitely distortion is there, no doubt in that one. Definitely distortion is there. but not up to the mark that you can notice. There is no need to notice. Okay, so it is clear. Next you see D2 configuration. One more electron definitely coming here. Same thing, very similar to the D1 and D2. D2 is also very similar to D1. One electron is present here. Now these two electrons are experiencing more repulsion than this. 100% there will be distortion, but not significant. So I am mentioning here D1 distortion is there. D2 distortion is there, but not significant. Not significant for us, you simply can remember. Definitely D1 and D2, there is a John Taylor distortion, but not up to the mark. Not significant, you can say it. Now coming to the very interesting D3. When D3 is there, the electron comes here. Up to here, I am not saying any weak field, strong field, or what you say, high spin, low spin. I am not mentioning anything because however the electrons are going to be here. 1, 2, 3. Done. So D3, when you see, all the orbitals are with say 1, 1 electron. So now all are equal. In this case, there is no John Taylor distortion. John Taylor effect is not applicable in this case. There is no John Taylor effect when 3 electrons are present. 1, 2, 3. Now all are equally with 1, 1 electron. All these orbitals are experiencing same repulsion. So there is no John Taylor effect. No John Taylor effect when there is D3 configuration. Now the interesting point will come. D4. D4. Where you want to give the 4th electron? Here or here? If you keep electron here, that's called high spin complex. High spin, why? Because number of unpaired electrons are going to be very high, very more. That you can say 4 unpaired electrons are there. If you keep electron here, definitely number of unpaired electrons will be only 2. So that's why this is called high spin complex. High spin complex are generally happening in what you say, weak field. Weak field Lagrange cases, you can expect high spin complexes. So high spin complex I am taking. Now high spin complexes. These are symmetrically filled, so no worries about this one. Here, dx square minus y square and dz square both are with more energy. Now in that, dx square minus y square is having 1 electron. This may be dx square minus y square or dz square electron present here and there. Okay, no issues about that one. But you remember, one orbital with 1 electron, the second orbital is without electrons. One orbital with 1 electron, the second orbital is not having any electron. So definitely there is a difference between them. When there is a difference in them and the ligands are approaching along the same axis, difference are coming along the axis only. So the orbital which is having 1 electron definitely experiences more repulsions and its energy is going to be more. Here John Taylor distortion plays very, very, very important role because the ligands are coming along the same, that means along the axis only, where the orbitals are present. The orbitals are now not equal. One orbital experiences more, one orbital experiences less repulsions. One will be with more energy, second will be with lesser energy. That thing happens here. So high spin complexes, D4 configuration, John Taylor effect is very, 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 very significant. So you can keep your 3-4 star marks. First question, D4 John Taylor effect is applicable if it is a high spin complex. High spin complex, sorry. If it is low spin complex, then what happens? Low spin complex, I am taking electrons from here, I am keeping here. Done. Of course, John Taylor effect is there. John Taylor effect is there, D4, but not significant. As we were saying, we are not worried about the T2G orbitals much. So I was saying the same things, I don't want to make you bored. D5, we'll go with D5. So D5, if the electron is coming here, low spin means a strong field, I am writing here as a strong field. Now again the electron is coming here, so this is again low spin. D5 configuration, John Taylor effect will be definitely there, but not up to the mark, not significant. So there is no need to think about this much. Okay. This is low spin. Okay. High spin complexes, if you see, this electron will be here. d phi, high spin means 1, 2, 3 completely filled, 1, 2 completely filled. Now both are having 1, 1 electron, so both are exactly getting the same repulsion from the ligand. So high spin d phi configuration, very interesting. There is no John Teller effect. There is no John Teller effect. The reason is the electrons are completely filled. Fine. Good. We'll go with d6. Sixth electron is coming here. Sixth electron, where it will go? However, we are going with the high spin now. We will go with the same high spin. The electron is coming here. 1, 1, 1, 1, 2, 1. Okay, now high spin complexes. High spin d6 if you see. 2 unsymmetrical. John Teller effect is there. Not significant. Not significant cases, you don't worry much. Okay, now it is definitely there. But no worries about that. If it is low spin complex, low spin means it is not here. All the electrons are going to be here only. d6 means completely paired here. So no unsymmetry, all are having equal. So low spin d6, no John Teller effect. Because exactly filled. So no question. Till now, d1, d2, it's there, not significant. d3, not at all present. d4 high spin, very important for us. So first question for you, in which of the following cases you can expect a John Teller effect? So first option, if it is d4 high spin complex, that's right. Remaining, not significant, not possible, not possible, not possible, not possible type only, not significant, not significant. In these two cases, not possible. So till now, whatever we have discussed up to d6, only one is important, that is d4 high spin. Only one. Okay. Next, d7. d7, I am going with the high spin, that is low spin complexes, that is strong field. 1, 2, 3, 4, 5, 6 completely filled. Our electron is coming here. d7. Low spin. d7. Is it symmetrically filled? No. Okay, now one electron is present here. This is not filled. So definitely there will be long bonds. Of course, there will be a lot of difference between them. This will be getting more repulsion. This is not getting repulsion. So there will be distortion. Definitely distortion will be there. John Teller effect can be seen here very, very, very clearly. It is going to be very important. So d7 low spin is again your favorite area. This is again your question. Low spin d7 definitely shows. Okay. Come to the next one. 7. Okay. If now I am going with the high spin. High spin d7. High spin d7 means, let me go one by one. 1, 2, 3, 4, 5, 6, 7. This is symmetrical, but it is not symmetrical. So definitely John Teller effect is there. Not significant. So I am taking only these two. Significant. Here it is there but not significant. Don't worry about this one. d7 is over. Let's come to d8. d8 configuration. d8, however we are writing high spin. So high spin d8 will say. High spin d8 means 1, 2, 3, 4, 5, 6, 7, 8. Completely filled here. So no problem. Completely half filled here. So no problem. So no John Teller effect is seen here. John Teller effect is not present in high spin d8. What about low spin d8? Low spin d8 means how it is going to be? Low spin. Okay. Low spin d8 means how it is going to be better? 1, 2, 3, 4, 5, 6, 7, 8. Is there any difference? No. Okay. 1, 2, 3, 4, 5, 6. This is completely filled. 1, 1. It is also exactly half filled. So whatever the repulsions it is going to get, it is getting the same thing. So no worries. It is also again there is no John Teller effect. No John Teller effect can be noticed in d8. It may be high spin or it may be low spin. Actually, there is no spin. There is no question of spin. That will be same. Now coming to D9. D9 electron is here. D9 again low spin, high spin, there is no need to discuss beta. D9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 100%. It is not clearly symmetrical. So it is having 2 electrons more repulsions, 1 electron less repulsions. So definitely John Teller effect is going to be much significant here. So you need to remember these three. First, high spin. Next, here low spin D7, high spin D4, low spin D7, and D9 high spin, low spin. There is no need to mention. Both are same. Okay, in both the cases it will be same. For example, 9 electrons are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or if you want to go with the strong field, 1, 2, 3, 4, 5, 6, 7, 8, 9. It will be same. So D9 configuration itself says it is going to be very effective in John Teller effect. So only 3 points you can remember. D4 high spin, D7 low spin, and D9 any spin. Okay, that means this D9 case there is no need to worry about that one. D9 means it shows. What about D10? D10 means 1 electron will be here. So that electron is going to come here completely filled. So no question of John Teller effect. So this is the maximum thing that you need to notice. Okay, that these kind of questions are going to be for you in your exams. Maximum to maximum question that can be asked beta. Which electronic configuration can show John Teller effect? Which can't show John Teller effect? What you need to remember is, look at your configuration D5 or D4 or D3 or D2 or D1 or D6, D7, D8, whatever it is. Okay, it is strong field or weak field. Just check. Above EG orbitals dx square minus y square dz square. In that, if the unsymmetry is there, that means 1 electron if they are present, no problem. If 1 electron is present, another is free. Otherwise, one is having 2 electrons, another is having 1 electron. In such kind of cases, there is John Teller effect. Otherwise, no question of John Teller effect. This is a possibility. Now, I will take you into axial and equatorial elongation. See here. Let us say this is a metal. 1, 2, 3, 4, 5, 6. Look at this bond. I want to make all of them same. This is, for example, let us consider all these bonds are almost equal length. This is a perfect octahedral like that. Now, for example, dz square orbitals are experiencing more repulsions. If your electron is present in the dz square orbital, okay, 1 electron is present in dz square, dx square minus y square is not having any electron. So, if the ligands are approaching along the axis octahedral, the same thing happens, and dz square is already having electron. So, between the electrons of the ligands and between the electrons of this metal d orbital, there will be repulsions, and in order to avoid these repulsions, the bond is going to be little longer. When this bond is going to be longer, this is called elongation. Which bond is getting elongation beta here? This axial bond is getting elongation. So this is called axial elongation. Generally, axial elongation takes place when the electron is present in the dz square orbital. Okay, dx square minus y square orbitals, when they are present, we consider them for the square planar geometry. So, if dx square minus y square orbital is having electron, if dx square minus y square orbital is having 1 electron, or you say 2 electrons, if it is getting repulsions, in such kind of cases, the metal will be there, and these bonds are going to be longer than these bonds. You can say like this. Now, these are the longer bonds, axial elongation. And in this kind of cases, you can say equatorial elongation. Equatorial elongation. Axial elongation, equatorial elongation. So when it happens beta, when the electrons are having, when the electrons are present in the dz square orbital, this happens when the electrons are present in the dx square minus y square. So simply remember, if the more number of electrons, or if the repulsions are because of the dz square, then generally that goes for axial elongation. Axial elongation. and దీన్ని prolonged elaborated type చెప్తున్నా. This is compressed. Okay, this is elaborated octahedral, this is compressed octahedral, so you can see. Or you can say axial elongation and this is equatorial elongation, easy words. Okay, this is because the electron is present in the dx square minus y square orbitals. When the electrons are present in the dz square orbital, axial elongation. When the electrons are present in the dx square minus y square, that is going to be equatorial elongation. This is the thing that is going to happen because of the John Taylor. Why this elongation is taking place? Very simple. Electrons repulsions will be there. When such kind of repulsions are there, the bonds are going to be little away. When they are going to be little away, the repulsions will be minimum. Okay, when the bonds are going away, that means electrons are distributed over a long area, so that the repulsions will come down. When the repulsions are less, automatically the stability will be more. Obviously, we were discussing in the first lines of this class, the symmetry disturbs and energy also. Symmetry is reduced and energy is also reduced. Symmetry reduced better, definitely. When these kind of things are there, symmetry is reduced. But along with that, energy is also reduced. When energy reduces means the stability will be increasing. The reason for the stability increase is the electronic pair repulsions between the ligands and the metal will be less, so that it is going to be more stable. This is all about the John Taylor effect, applicable for NEET examinations and JEE entrance examinations. If you know these lines, that is going to be enough. Just to see which configuration is going to show and what are the consequences of this. John Taylor effect means it is not getting any problem to the molecule. It is giving a solution to the molecule, so that it is going to be more stable. Okay, or the concept of this is very simple. Because of the electronic repulsions, there is a distortion. When we are discussing sp3d3 hybridization, we say the shape of the molecule is distorted octahedral. The meaning of distortion or distort means it is not in the regular one. Okay, it is not in the regular shape, so there will be some distance, some disturbances. This is what increased. Okay, now equatorial increase as well as this is axial increase. John Taylor effect. Chalo, next time we'll meet with some other topic.